Okay, so you have started recording and I will start recording on this backup thing. Okay, now you're all set. So on Monday, I was discussing this particular aspect of our theory, which had to do primarily with the deformations, with the nature of the deformations. And first of all, we had taken a look at what happens in this XY plane, where under transverse loading, our beam, it undergoes this kind of a bending deformation. It curves upwards. And the same beam, if you look top down, meaning into the XZ plane here, it will look like this. So it does not curve away from this straight line. Okay, it does not become like this. It was originally straight and lying along the x-axis or lying parallel to the x-axis. It remains parallel to the x-axis even after deformation. Now, I had highlighted in particular about this Euler-Bernoulli beam hypothesis, which becomes a theory in light of the fact that many of the underlying assumptions, even though they may seem rather restrictive, despite that, in many of the actual engineering situations, this Euler-Bernoulli beam hypothesis, the underlying assumptions, they're actually borne out correctly. Meaning that the predictions from this theory, they do match with the experimental results. So this is a rather successful theory, one of the most successful theories, in fact, in not just mechanical engineering sciences, but in all of the engineering sciences, because it has stood the test of time. So nothing tells the success of a theory more than how it has stood the test of time. Of course, as you start to go into more kinds of adventurous geometries, which people tend to do nowadays, the limitations of the Euler-Bernoulli beam hypothesis, it comes to the fore. So people have to go on for more sophisticated theories. But that is certainly beyond the scope of this kind of an introductory course on mechanics of materials. So we will satisfy ourselves with studying and understanding the Euler-Bernoulli beam hypothesis and the mental muscles that we will develop through trying to understand the Euler-Bernoulli beam hypothesis. That will stand you in extremely good stead once you go on to those more advanced theories in later classes. So you will see that almost throughout this entire course, this one semester course, we will be dealing with this Euler-Bernoulli beam hypothesis and things around it. But later on, when you go on to more advanced classes, you will see that given that those understanding muscles have already been developed, you can quickly pick up, learn, and apply many of those other advanced theories at the same time. Okay, so that is the whole plan of your education. All right, that is for later. For now, we have to deal with this theory. We have to understand it and we have to apply it. So we were dealing with, or we were talking about the various implications of these underlying assumptions as far as the strains are concerned, the various strain components are concerned. We had mentioned that epsilon yy equal to 0 and epsilon zz equal to 0. It mainly follows from this particular aspect of the assumption that plane sections do not change dimensions. The gamma xy equal to 0, it followed from the fact that these right angles, which were originally right angles in the undeformed configuration, remain so even after deformation. Even though the thing has bent upwards, this right angles remains right angles. So the gamma xy, it remains equal to 0, or it is 0. Gamma xz is also equal to 0 because looking down into this xz plane, these two line segments, any of these two line segments which are individually parallel to the x and the z axis, in the undeformed configuration, they were at right angles. Even after deformation, they stay at right angles. So gamma xz is equal to 0. And finally, the gamma yz is also equal to 0 because if you consider a plane like this, each of these transverse sections which we have sliced off, they are, as a result of the entire beam curving upward, the entire plane section, it rotates upward like this so that it no longer is perpendicular like this, but within the confines of this plane, this angle, this angle, this angle, this angle, they do not change from the original 90 degrees. So originally it was 90 degree, even after deformation, even after the thing has rotated upward, it does not change from the 90 degrees. So the gamma yz is also equal to 0. Now you see, we have talked about all the different strain components, but for one, except one. What is that? That is the epsilon xx. And I had at the very end of the last class, I had mentioned that epsilon xx is not going to be equal to 0. And that will be the starting point of the rest of our discussions, because the entire game, the entire development of the theory, it depends on the fact that epsilon xx is not equal to 0. Now, before proceeding onward, what is the implication of this epsilon xx not equal to 0? What is the story behind this? Well, in a very gross sense, it is very easy to understand. You see, you consider any line segment which is lying along the or lying parallel to the x-axis. Okay, because this thing is bending upward like this, it may be evident to some of you that there is a change in the length. Okay, there is a change in the length. It may be evident to some of you. It may not be evident to all of you. So we will go into the details of why this is not so. The epsilon xx is not equal to 0 in a moment. But before we go into that, I will like to discuss a little bit about the stresses itself. So let us first consider the shear stresses. You see this gamma xy equal to 0, gamma xz equal to 0, gamma yz equal to 0. So all the shear strain components, they are 0. The immediate implication of this is that, so tell me, you guys tell me, I have been speaking continuously. You tell me, what is the implication of this shear strains being equal to 0? Implication in terms of the stresses. Does it guarantee for us that any of the stress components should be equal to 0, following on from these things, that the shear strains should be equal to 0? Please tell me.
Sir, if we consider in the elastic region, then we can say that the shear stress is 0 in all these three cases.
Yes. First of all, kudos to you for saying that particular statement at the very beginning, that if we assume them to be within the elastic region, that is very important to state. But within the scope of our syllabus for mechanics of solids, unless anything specially is mentioned, we will always assume that we are very much safely within the elastic zone. Okay, so what you are saying is perfectly all right. That if we accept these three things, then it immediately follows that the corresponding shear stresses are also 0, meaning specifically that sigma xy or tau xy is equal to 0, tau xz is equal to 0, and tau yz is equal to 0. It follows immediately from the fact, or if you go back to your first year BEM, you had learned about those relations where we said that tau xy is equal to g, g being the shear modulus, tau xy is equal to g xy, gamma xy, tau xz is equal to g gamma xz, and tau yz is also equal to g gamma yz, g being the shear modulus. So because these things are 0, that is why all of the so gamma xy is equal to gamma yz is equal to gamma xz, or zx, doesn't matter, is equal to 0. It implies immediately that tau xy is equal to tau yz is equal to tau zx equal to 0. Okay, because you have things like tau xy is equal to g gamma xy, etc. Etc. means the other two equations. What about the normal stresses? Meaning sigma yy, sigma zz, sigma xx. Tell me. So what I want you to think about is the generalized Hooke's law.
So sigma yy and sigma zz will be 0, but sigma xx cannot be, because epsilon xx is not equal to 0.
So right. So why do you say that sigma yy and sigma zz are going to be equal to 0?
Sir, as we discussed previously, the in the Hooke's law is valid, and from that the ratio of stress and strain is constant.
But there is a little. Yes, somebody else is saying something. Please tell me.
Sir.
Hello.
Hello, sir.
Yes. Somebody else
If
was.
there was some Eyy or like epsilon yy or epsilon zz, the plane sections would change the dimensions.
I cannot hear you properly, but I think what you're saying is correct.
Sir, I was saying that the plane sections would change their dimensions if this epsilon yy or epsilon zz was not zero.
Are you talking about the Poisson's ratio thing?
No, so the third constraint in that Euler-Bernoulli.
No. So I'm asking purely in terms of the generalized Hooke's law formula that you learned in your first year. Okay, so whatever we had to say regarding the deformations, we have already said in terms of these strain components. Now, given this information, so we are accepting this information. Based on this information, I want you to think about the stresses. And when you want to think about the stresses, the only way you can do that is by connecting the strains to the stresses. And for that, you will have to take the help of the stress-strain relations. The stress-strain relations which you studied in your first year are the generalized Hooke's law. So that is what I'm asking you to think about.
Sir, excuse me, sir.
Yes.
Sir, I was wrong previously. So due to the presence of the Poisson's ratio, all the components will be non-zero.
Yes. So you are theoretically correct. Okay. You are theoretically correct now, but in reality, what you said earlier was correct. Okay. So now that you are sufficiently confused, let me tell you what is happening. So it's like this. You see, the generalized Hooke's law, it tells us things like this, that epsilon xx is equal to 1 by E sigma xx minus nu sigma yy plus sigma zz. Fine. Similarly, you will have epsilon yy is equal to 1 by E sigma yy minus nu sigma xx plus sigma zz, and epsilon zz is equal to 1 by E sigma zz minus nu sigma xx plus sigma yy. This is the general theory, the generalized Hooke's law. Okay, in fact, these relations tau xy is equal to g gamma xy, tau yz equal to g gamma yz, and tau zx equal to g gamma xz, those three relations, together with these three relations, they are actually the generalized Hooke's law. Okay, we have no problem with those shear stresses. So now we are considering these normal stresses for which there is a problem. What I want you to think about is that these are the relations connecting the strains with the stresses. Okay, so on the left hand side you have the strains, but equivalently it is very much possible to just solve for the stresses in terms of the strains. Okay, so what I'm saying is that from these three things you can write the sigma xx, in terms of, so it's something like a function of epsilon xx, epsilon yy, and epsilon zz. Okay, and you will find that this is a linear relationship. Similarly, the sigma yy will come out to be a function of epsilon xx, epsilon yy, and epsilon zz, and sigma zz will also come out to be. So maybe this is f1, this is f2, and this is f3 in general. Okay. So you'll have these three relations. Now what is going to happen is this, that we have already said that epsilon yy is equal to 0. Epsilon zz is equal to 0. Okay. So similarly here, this is 0, 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 this is 0. Now, these relations will shape up in such a way that because epsilon xx is not equal to 0, you will find that sigma xx is not equal to 0. Because epsilon xx is not equal to 0, theoretically you will find out that sigma yy is not equal to 0, and epsilon xx not equal to 0 will imply that sigma zz is also not equal to 0 theoretically. However, the way these relations will appear will have the influence of this Poisson's ratio here. Okay, you can actually solve for this and see. Okay, you will see that this nu will appear in a will influence the values of the sigma yy and the sigma zz. In fact, you will find that the magnitudes of these two things are going to be less than this. Now, as part of the Euler-Bernoulli beam hypothesis, this is an extra kind of assumption that people do, is that these are small, sigma yy and sigma zz are smaller than sigma xx. What they do to make their life easy is they just assume that sigma yy and sigma zz are not just small, in fact they are so small that for all practical purposes they're neglected. Okay, and this is where there is an internal inconsistency. Okay, internal inconsistency means that on the one hand, you are assuming the truth of the generalized Hooke's law, but on the other hand, what the generalized Hooke's law is telling you, you are not willing to accept it. I repeat, there is an internal inconsistency in this theory because on the one hand, you are assuming that the generalized Hooke's law is true. But on the other hand, you are saying that no, what the generalized Hooke's law is telling me, partially I will take what is convenient for me. But on the other hand, regarding this sigma yy and sigma zz, because it is making my life a little bit difficult, I will not take it. I will consider it to be 0. So what in reality this is equivalent to doing is that you perhaps remember that in your +2 in your senior secondary, as part of your materials chapter in physics or something like that, you had learned about the Hooke's law and not the generalized Hooke's law, where you just said that sigma is equal to E times epsilon. The normal stress is just equal to the Young's modulus times the strain. If you accept the stress-strain relation in this particular form, then yes, this sigma yy will simply be equal to the Young's modulus times the epsilon yy, and because epsilon yy is 0, sigma yy is conveniently 0. Similarly for sigma zz, if you take it to be equal to the Young's modulus times the epsilon zz, so sigma zz is conveniently becoming 0. But within the scope of the generalized Hooke's law, which is much more general as the name suggests, the sigma yy and sigma zz being 0 are not strictly true. Nevertheless, we proceed with this restrictive, rather inconsistent looking assumption. And again, the argument for doing such a thing is that it may look internally inconsistent, it may look untrue or false, but the results that you get out of it, they somehow magically match with the experiments to a great extent.
Sir?
Yes.
Sir, like while designing the bridges, sir, like these values might not be so small as what we are thinking. So, in that cases also, do we neglect them?
So it's like this. Okay, since you started talking about building bridges, you see, the business of building bridges, it is far older than either of Euler and Bernoulli. Okay, I can tell you that Euler was a Swiss mathematician, but he did most of his works in St. Petersburg, which was in Russia. And you can imagine that when he traveled from Switzerland to Russia, he had to cross many bridges. So bridges existed even before Euler was born. Bridges existed even before Jesus Christ was there. Okay, it is that old. Okay, so the business of building bridges, it was taking place without people knowing much of mathematics. Of course, those bridges, the construction of those bridges was very inefficient in terms of the amount of material that had to be used, in terms of the design that had to be made. Now, when these mathematicians came along and provided these theories, it provided a basis for engineers to design the bridges in a far more efficient manner. Believe it or not, based on these kinds of very basic beam theories, the first proper large-scale engineering structure that was built based on beam theories, do you know what it was? It's like a quiz question. Based on this, yes, Eiffel Tower. I have said this before, but it was the Eiffel Tower. Okay, before that, most of the large mega structures of the engineering world, they were built just on the plain old good engineering sense and like the apprenticeship of the people. Okay, it was purely based on experience and knowledge handed down from one generation of engineers to another. Okay, it was more like an art rather than a science. But the Eiffel Tower was the first engineering structure where it was built based on certain mathematical theories. Of course, it was built in the 19th century, if I'm not wrong, and the theories that were present at that time were still at a very basic stage. Nevertheless, the Eiffel Tower is still standing. Okay, it's a mega success of the engineering world. Now, since you are talking about building bridges nowadays, you can rest assured that maybe for certain part of the structure, the Euler-Bernoulli beam hypothesis would be decent enough to be applicable. But in many of the more advanced, sophisticated parts, it would be far from satisfactory. There would be other theories of beams which would be used. Furthermore, please do not think that just because we have managed to learn something about beams, it is the end all of it. Meaning to say that this is just the statics part. When you build a bridge, one of the biggest challenges there is to deal with the loadings from the wind. And as I was answering to one of your batchmates' questions yesterday on MS Teams, for the simple case of designing an electric lamp post that is standing on the street, it is under the purview of vibrations of structures also. So you can understand that a bridge which is spanning across a river, which is subjected to various kinds of difficult and very severe wind loads, the vibrational aspect of it would be extremely important also. So there are a lot of sophistications which goes into building those mega structures. The skyscrapers that are built, that also is, they also face wind loads. They are time varying they are very severe, and various kinds of theories go into designing them. It is not just one aspect. So first of all, Euler-Bernoulli beam hypothesis is a good starting point, but there are more advanced aspects of these beam theories. Secondly, the beam theories themselves, from the statical point of view, are just not sufficient. You have to bring in many of the dynamical aspects from fluid mechanics, from vibrations, to complete the entire design process. Okay, so which is why you are not allowed to build bridges just after your second year. I hope what I'm saying, you're getting what I'm saying. Okay, so with that notion, let us first try to learn how to crawl like a baby before we can learn how to walk and then to run. Okay, but these are extremely important steps. Nobody can learn how to run without first learning how to crawl. So first let us learn how to crawl. All right, so we are saying that these two things, they are going to be assumed to be zero. So assumed to be zero. We assume them to be zero with the understanding that they are strictly not true, but they kind of work. So all in all, what we are obtaining is this, that epsilon xx is not equal to 0 and sigma xx is not equal to 0. The rest of them are 0. This is the big implication, or the final implications, as far as the strain components and the stress components are concerned. Now with this thing, we have found out that they are not 0, but what are they? Okay, not 0 is, easy to say, but what is the value? How do we go about doing that thing? Okay, so that is where we actually need to deal very specifically with the geometry. And in the previous class, somebody had actually initiated the discussion very nicely by asking that if we go to the previous diagram, I had drawn it like this, and one of you had mentioned or asked that is it perhaps okay to assume that this is like a circular arc? And I had mentioned that yes, that is going to be our starting point of developing the theory, of arriving at the formula, and that is exactly what we are going to do today. Okay, so we consider a beam like this. So when I say a beam like this is actually a part of a beam. And what we say, and I'll draw this in a slightly exaggerated fashion here in order to make the diagram clearer. This is an extremely exaggerated diagram, okay? So usually the kinds of beams that you see in day-to-day engineering practice, for example, the kind of beams that will be present in the very roof of the room that you are sitting, would not be curving upwards with such a huge curvature, okay, or such a small radius of curvature. It won't be curving up like that. There'll be only a very minuscule curvature or a very, very large radius of curvature. Okay, so you can barely see the beam bending upward, but it is bending upward. Okay, as you load it, it is bending upward, but not in this kind of a spectacular fashion. But we want to have this kind of an exaggerated cartoonish diagram in order to do the derivations in a clear and clear fashion. Okay, so think of it like this. Initially, let's say that this is something like AB. Okay, so this point is A, this point is B. These are not the corner points I'm talking about, okay? Some point very close to the top, and this A and B are selected such that if I draw a line like this, it is parallel to the top surface. In the same fashion, I will consider a point here and another point on the right hand side. Let's call them P and Q. Again, the line segment PQ is parallel to the top edge and the bottom edge. After deformation, let's say this point is A dash, this point is B dash. And we again join them up such that they are following the curvature of this thing, of the top surface. This here is P dash, Q dash, and we join them up such that again they follow the curvature of the bottom and the top surfaces. Not the best of diagrams, but hopefully I'm being clear here. All right, now you tell me what is the relationship between A dash B dash and AB? Is it larger than AB? Is it smaller than AB? Is it equal to AB?
Smaller than AB.
Smaller than AB. Yes. What about P dash Q dash and PQ?
P dash Q dash should be larger.
P dash Q dash will be larger than PQ. All right. Now you see that over this height, or if you want to call it a depth of the beam, you have one line segment which is smaller than its original length. You have another line segment which is larger than its original length. Original length means the length which it had in the undeformed configuration. Now, this is smaller, this is larger. Does it not logically imply that there will be at least one transition point in between them? Meaning to say that at that transition point, it should be such that even in the deformed configuration, the line, this curved line segment that we are going to draw, it is going to be equal in length to the original undeformed length. Does it not logically follow? Yes or no? At least one transition point.
Yes, sir.
Okay, let us say that such a line segment is this. And let us call this M dash, N dash, with the understanding that the corresponding points in the undeformed configuration were this, M and N. I have told you just now that there should be at least one transition point between them, and there is nothing, mathematically speaking, okay, in a purely mathematical sense, there is nothing stopping us from probably imagining that there would perhaps be more transition points. Okay, at least one can imagine there should be an odd number of transition points. Now that is purely mathematically speaking. But this is not purely mathematics that we are doing. We are doing things related to an engineering structure, very much an engineering structure. So we will appeal to our practical experience and say that indeed what actually happens is that there is only one transition point. Okay, you do not have these odd number of transition points, where odd being a number greater than 1. It's not like that. Okay, you don't have 3 or 5 transition points or 7 transition points. You have only one transition point. So there is only one unique line segment which deforms in such a fashion that its length remains unchanged, meaning that M dash N dash is going to be equal to Mn. Now this M dash N dash, or this Mn, or this A dash B dash, this P dash Q dash or PQ, whatever, all of these we have been referring to as line segments because we have been looking at this two-dimensional picture of the beam, or this two-dimensional projection of the beam. And let us not forget that this projection is in a plane which is parallel to the XY plane, because as per our original choice, this is X and this is Y, and coming out of the plane of the screen is the Z. Similarly, here also you will have this this thing like x and this thing like y. So this is everything in the xy plane. But in reality, this is a three-dimensional structure. So this MN line segment that we're seeing, or this PQ line segment that we're seeing, or A dash, B dash, P dash, Q dash, whatever, they're actually not line segments, rather they are themselves planes. If you consider the depth into the plane of the screen, they are like planes. So this M dash N dash line segment, which is actually the M dash N dash, or the surface or the plane associated with this M dash N dash projection, that surface, that curved surface, is referred to as the neutral surface. Okay, this M dash N dash, or equivalently the Mn, it is referred to as the neutral surface. Neutral means there is neither a change in its length in the positive direction or in the negative direction. Simply speaking, the neutral surface does not change in length. Okay. The moment you recognize the existence of such a neutral surface, the rest of the derivation becomes a pure matter of geometry. Okay, geometry and a little bit of algebra. So what we want to do here is we want to recognize, or we want to determine the expression first of all for the epsilon xx, because we have already understood from our previous slide that epsilon xx is not going to be equal to 0. It's a non-zero entity. So what is it? So epsilon xx, it has to do with changes in the length, or relative changes in the length parallel to the x direction. So suppose I consider epsilon xx in terms of the changes in lengths that are undergone by a generic line segment such as our AB, as it goes from AB to A dash B dash. So can we not say that epsilon xx is going to be generally determined by an expression like A dash B dash minus AB divided by AB? Can I not write like this, that epsilon xx is going to be equal to A dash B dash minus AB divided by AB? Now, many of you will protest that earlier I had made a big fanfare about saying that epsilon xx is a point entity. Therefore, we should be focusing our attention not on the entire line segment, rather on a single point. But for these kinds of very homogeneous or uniform deformations, it does not really matter whether you are focusing your attention at a point or over the entire line segment, because whatever is happening here is happening here is happening here, so that whether you take it macroscopically or microscopically at a point, it will give you the same result. So many of you are doing courses like partial differential equations, and let me tell you that epsilon xx, very mathematically speaking, would not be expressed in this kind of a gross fashion. Rather, it would be expressed like the first derivative of the displacement along the x direction with respect to the x derivative. So it would be something like del u del x, where u is the displacement in the x direction. But at this point, you do not have to worry about those kinds of expressions. Those will be taught properly to those students who would be taking the specialization of mechanical systems design. It is going to be a mandatory course for you, ME 40605, called Applied Elasticity. There you will get all the deep details of such kinds of things. Nevertheless, I would like to draw your attention at this point to the fact that in fluid mechanics, at least the mechanical guys, the ME guys, you are probably learning as part of your kinematics chapter things about strain rates. And there you will learn something like epsilon xx, or maybe they call it exx. that will be equal to del Vx del x, where Vx is the velocity in the x direction, and Eyy will be equal to del Vy del y, and other things like that. So there is a nice connection between those kinds of expressions and the kinds of expressions that I just told you about. But again, I'm telling you, as far as the scope of our syllabus is concerned, it is not there. Okay, so you don't have to worry about it right now. So coming back to this thing, we can write about it like this, but it does not help us if we just keep it in the form of this a dash b dash a b and a b. We have to have a more general way of depicting the epsilon xx. How do we go about doing that? Well, the trick is like this. You see this AB in the numerator and this AB in the denominator, it is the undeformed length of the A dash B dash. So if you go back here, this is the AB. Now AB happens to be equal to MN. Because of the particular beam geometry that we're working with, AB is perfectly equal to MN, is perfectly also equal to PQ. But the fact of the matter is that it is equal to MN. Now the good thing about it is that MN does not change in length. Okay, so even if you are focusing your attention on this deformed configuration, we can say that AB is equal to this M dash N dash, because M dash N dash is equal to MN and MN is equal to AB. Okay, so we can say that AB is equal to MN, but that is also equal to M dash N dash. So referring to just this deformed configuration, it is very much possible for us to write things in a very general way by recognizing that AB is equal to M dash N dash. But then again, the question remains, how do you actually write this expression in a general fashion? Well, for that, we will appeal to that earlier statement that we had made, that we are going to understand this deformation to be in the form of a circular arc. And if you do that, things become immediately clear. You see, what we can do here is that we can consider this particular curved line M dash N dash to be a circular arc having the radius of curvature rho. So we depict it in this fashion. This point up here, let's call that C. C is the center of curvature of this circular arc. In fact, this circular arc is such that this, all these circular arcs are such that they are all concentric at C. I repeat, all these circular arcs A dash B dash, M dash N dash, P dash Q dash are such they are concentric at C. So this rho is the radius of curvature. What we also say is that the angle which is subtended by this kind of a bent figure, that the angle that is subtended at C, this entire angle, that is theta. With these pieces of information, you guys tell me what should be A dash B dash. This is now a matter of pure geometry. One hint I will tell you, you have to bring in or you utilize the fact that A dash B dash or M dash A dash B dash will be at a distance of y. Will be at a distance of y from M dash N dash. I repeat, A dash B dash will be at a distance of y from M dash N dash. And for that we can actually
rho minus y into theta.
Rho minus y into theta. So let me first write that down and then I can clarify your doubts if you have any. So A dash B dash is rho minus y times theta. AB equal to M dash N dash, that is simply going to be rho times theta. Okay, and please note, when I'm writing these things, I am basically utilizing whatever you have learned in your high school geometry like this. S is equal to r times theta, where r is the radius of curvature of the arc, theta is the angle subtended by the arc at the center of the curvature, and s is the arc length. So all of these, they are the arc lengths. A dash B dash is the arc length, AB or the M dash N dash is the arc length. So this is rho theta, this is rho minus y theta. And in the denominator also, we have rho theta. So if you just carry out the algebra, what this becomes is minus y by rho. This is the expression that we are looking for. Now let us get back into this picture and be very, very clear about what we are doing. First of all, you note that if I claim that this curved line segment A dash B dash is at a distance of y from M dash N dash, it basically means that in the undeformed configuration, I am considering my x-axis to be along the MN. I repeat, such a statement that A dash B dash will be at a distance of y from M dash N dash will be true only and only if I have assumed that I will set up my x to be lying along the MN. Correspondingly, in this diagram also, not counting about the curvature, we can understand that x is along this M dash N dash. Okay, in the deformed configuration, it doesn't make much sense to say a thing like this, that a line segment which is supposed to be straight like this x direction is along the M dash N dash, which is why I'm referring to this undeformed configuration that x is along the MN. Furthermore, you note that y is pointing upward. Since y is pointing upward, that is why I have to subtract this thing, rho minus y. Had I taken a point below this, then the thing would have been different. Okay, anyway, so we have this epsilon xx is equal to minus y by rho. The moment we have this, we should be very happy with ourselves because we have now found an algebraic expression for epsilon xx. But do remember that we still do not have a clear-cut picture about this rho. So do not feel overly happy about yourself. So what we'll do is we'll go to the next slide and try to figure things out, what we can do. So we need some extra pieces of information. The good news is that we already have those pieces of information in our hand. I'll create a new slide in between. Okay. The first thing that we are going to do is to again write, of course, this epsilon xx is equal to minus y by rho. And then from this, we are going to say that sigma xx is going to be equal to E times epsilon xx is going to be equal to minus E y by rho. So now we have an expression for the sigma xx also. But that does not change the fact that we still don't know about this rho. What do we do about this? Definitely, we are at a stalemate again, and we need an extra piece of information in order to proceed. What is that extra piece of information? Can anyone say? So you go back to, I will go back to the first of the slides, okay? I'll go back to the first of the slides. You see, here, I have not written any formula. There is nothing here that you can use. Let us go to the next slide if there is anything here. Look at here. This is also bending. Everything that I have written here is also true to whatever we are saying. At this point, we were stuck. So we went on to talk about the deformations. Now we have stopped talking about, we have managed to talk a lot about the deformations. We have managed to find an expression also connecting the deformations to the geometry and everything. Now we are at a stalemate. Can we not use this? Because you see, this bending moment M is something which would be known to us. So perhaps there is some hope for us that if we use this kind of relation, then we can perhaps find out the rho in terms of known quantities. All right, so let us quickly go back and write out an expression involving this sigma xx and involving this m, and y of course is just the coordinate variable. Let's see what it does. So we rewrite that expression. Now m is equal to minus, I'm just rewriting this expression that I wrote in the slide number 2 here. Sigma xx I will simply substitute from here. Minus minus plus. All right. Now you see we are at a very nice situation. First of all, you understand that this integration is over the entire area of a particular transverse cross section. So this is over the entire area of the cross section. So we are only talking about, so if you consider the beam, we are talking about one particular cross section. This is the one that has the area A. That area A, we are over that area that we are doing this integration over that entire cross section. Now over that entire cross section, no matter how difficult the geometry of the beam may be, how sophisticated the nature of the variation of the materials may be, or whatever, it must be true that on that particular cross section, as long as there is no variation along the height, okay, as long as there is no variation along the height, and mind you, in certain kinds of beams, there will be variation in the material properties over this height, and we are going to do certain problems like that. So right now, there is no variation. Okay, so everything here is uniform, meaning to say that this Young's modulus E that can be taken out of this constant, this integration. So we'll do that. E we have taken out. What about this rho? The rho depicts the radius of curvature. And again, we have already seen in the previous slide that as far as the radius of curvature is concerned, it does not matter which point along this any particular cross section we are lying. Okay, so if you consider a point here, or a point here, or a point here, anywhere the radius of sorry, I should not say like that. At a particular cross section, this rho depicts the radius of curvature considering the neutral surface. So at a particular cross section, definitely you do not have any variation of rho over the cross section. Okay, you may in certain sophisticated situations have some variation of rho along the length possibly, but at a particular cross section, rho is just rho. It's a unique value. So for the integration, for the purpose of the integration, we are good, and we can take it out of the integral. So what we are left with is integration of y square dA, integrated over the area of the cross section. Now this particular entity, who can tell me what it is?
Moment of inertia.
That is the, please tell me again, I could not hear you.
Moment of inertia.
It is the moment of inertia or the area moment of inertia. I do not particularly like the term moment of inertia because already in your +2 you have come across the moment of inertia, and where that had to do with the density, the mass density. Okay, there is nothing to do with the mass density here. We are only and only talking about purely the geometrical aspect here. So a better terminology is the area moment of inertia, or even better, the second moment of area. The area moment of inertia or the second moment of area. Please note that when I write a thing like second moment of area, you must immediately suspect that there should also be a thing like a first moment of area. And in fact, there is such a thing. So if you write an expression like this, integration y dA, this is the first moment of area. Can you tell me in what type of calculation we need to utilize this first moment of area? And this is very much relevant for beam theory. I'm not just asking you for general knowledge purpose.
So non-uniform load.
Even more basic than that. All of you have done this.
Center of mass.
Right. So what is the, so center of mass again has to do with the mass, but in terms of the pure geometrical counterpart of the center of mass, what is there?
The centroid.
Absolutely, very good. So the pure geometrical counterpart of the center of mass concept is the centroid itself. So in the calculation of the centroid, you have to use something like this. Okay, and that centroid calculation is something which is absolutely basic and important to our calculations of these beam theory formulas. And you will see that in the problems. So overall, what we are ending up is this: EI divided by rho, where this I is a very standard way of denoting the area moment of inertia. Okay, so this is I. Always and always use this type of symbol. Okay, everyone will understand anywhere in the world that I represents the area moment of inertia or the second moment of area. So overall, what we are getting is this: M is equal to EI by rho. This is one of the most important things you will learn in all of mechanics of materials or mechanics of solids. M is equal to EI by rho. Sometimes people also write this as M rho equal to EI. It's a very nice kind of formula, very easy to remember also. Now, fine, we have found out this thing. You may also say that rho, the unknown entity, is equal to EI divided by M. It's a nice formula because it gives us an expression for this radius of curvature of the neutral surface in terms of known entities. E, the Young's modulus of the material, is a known entity. I, the second moment of area, is a known entity because given the geometry of the cross section, you can very well calculate it. And M is the applied moment or the bending moment which is felt at a particular cross section of the beam. So whatever you have done in your previous week, where you found out the value of the shear force and the bending moment anywhere within the beam, given a certain way of loading of the beam, with that knowledge, you are confident that you face any beam, as long as it is a statically determinate one, you can find out the value of this bending moment at any particular cross section. So E is known, I is known, M is known, you can find out rho. That is why this is a very nice formula. Other thing nice about it is a very simple formula. Okay, there is no non-linearity into it. It's a nice linear thing, very, very good. But there is still that lingering question which is pricking in our brain that all this is nice and good, but what happened to sigma xx? We are still not having a formula in our hand that will enable us to calculate sigma xx, but actually the job is done. Okay, you just see here, sigma xx is equal to minus E y by rho. E is known, y is known, rho is now known. We just have to substitute it properly. Okay, so very quickly, I will do this thing. In fact, this is so important. Let me go to the next slide. We should give it its due respect. So sigma xx is equal to, we have already written this, minus E y by rho. And rho we have just found out is going to be equal to EI by M. So we substitute this here, minus E Y E I by M. So this is equal to minus M Y by I. This is the expression that we are looking for. This is the expression that we are looking for. So as far as the theory part of our current chapter or the current topic is concerned, we are done. Essentially, we are done. There are other more nitty-gritty aspects of it which we'll deal with, but this is what is referred to as the bending stress. This sigma xx is the bending stress. Sometimes this entire form or the flexural formula. That's it. So sigma xx has now been expressed in terms of known entities.
Sir,
I is the second moment of area of a particular cross section, and again M is known very well at a particular cross section. Yes, somebody was saying something.
yes, sir, like sigma xx, so here we have derived a formula, but sir, like while in bending of a beam, the beam will bend, like it will curve upwards or like in any way. So like the stress in the upper part will be like it would be a pulling stress, and then in the bottom part it would be a pushing stress. So how do we account for that?
Very good. Except that you just said the opposite thing. So it's like this. You see this thing is curving upward like this.
Yes.
It is curving upward like this. I'm just drawing in small whatever I had drawn earlier so that I can carry out the discussion in relation with this thing present on the left hand side. So we have already seen that this is becoming shorter in length compared to the undeformed configuration, right? If you consider in physical terms a fiber of a beam, so all this while I have been saying line segments, but in physical terms of the beam, so a fiber getting shortened in length as part of the bending deformation, it basically means that it is undergoing compression. What you had said was that it will experience some kind of pulling. No, it is not going to experience pulling, rather it is experiencing pushing. Okay, so the fiber at the top in this kind of a curving upward business, it is experiencing a compressive force on it. But the fiber on the bottom, that is getting elongated. So it is this fiber which is experiencing that pulling action. Okay, it is under tensile stress. This top one is under compressive stress. Now that is the physical understanding behind it. You are perhaps thinking, how do we reconcile that physical understanding of the compressive nature or the tensile nature with this formula? Is it not?
Yes, sir. Yes.
Okay, so you substitute the appropriate value of y. When I say appropriate value, it means with the appropriate sign. So earlier I had said that this is our y. If y is positive, which it is for this kind of a fiber lying above the neutral surface. So remember, our neutral surface is somewhere here. So a point which is lying at this here, it will have a positive value of y. Okay, so for point lying above the neutral surface, y is greater than 0, which implies that sigma xx is less than 0, which means that this is compressive in nature. Again, for points lying below the neutral surface, y is less than 0, which implies that sigma xx is greater than 0, because then y, the algebraic sign of it, would be coming with a negative thing. So that minus and this minus would be giving us a minus, positive thing. So sigma xx is positive and it is tensile in nature. So I hope this is clear. In fact, many a time, in fact, in your textbooks also, they will be depicting the distribution of stresses over a particular cross section. Please note that this here represents the point where the neutral surface cuts this transverse section. So I'm considering a thing like this. It cuts a cross section like this, and this is the point that I have depicted here. This is that same point. So what they do, represent the compressive stresses in this fashion. Okay, so these are the compressive stresses, and then below the neutral surface, where you have the tensile one, you will have the stresses depicted like this. So these are the sigma xx. All right.
Yes.
Okay, good. So since I've been speaking almost non-stop, let me take a 2-minute break and then we'll regroup and continue with our discussions. Okay, and very quickly we'll try to go into the slight discussion of the problems. Okay, so let's take a 2-minute break. All right, let us begin again. So we have found out this Flexure formula, and we have found out this relation or this algebraic expression for this sigma xx. Let us not forget that we were able to achieve this kind of an expression or arrive at this kind of an expression following on from this equation which we had derived on Monday, that this connection between the m and the sigma xx. So let me go back to that second slide once again and bring to your attention once more that we do have this equation which we have already utilized. But what about this equation? This other equation that we have, is it perhaps possible that this second equation, it provides to us another something important which we perhaps may have missed? Let us try to do this. Okay, so what we have here is that 0 is equal to integration sigma xx dA. Basically, it is telling us the connection between the total axial force which is exerted on the beam, which is actually 0, with the normal stresses integrated over the area. We now have an expression for the sigma xx, which is minus my by I. Again, as per our previous discussion, the second moment of area is a constant value as far as the integration over a particular cross section is concerned. Similarly, the bending moment has a unique value at a particular cross section. So over the cross section, it is not going to change its value. Okay, it may change its value along the length of the beam, but since we are taking this integration to be over a particular cross section, this m value is not going to change. It is a constant with respect to this integration. So m and I can both be taken out of the integration. In fact, since you have a 0 on the left hand side, this m and I, they are certainly both not 0. So we can actually write that integration y dA is equal to 0. What is the implication of this? This is tremendously important. Okay, as far as our actual calculations are concerned, please do not think that these are just some kind of some intellectual exercises that we are carrying out, which is fun to do, but which has no significance to engineering calculations. It is not like that. It is absolutely essential, in fact, to the first step of the engineering calculation that you will need to do in order to solve your problems and beyond that also. So what is the implication of this?
So the neutral line passes through the centroid.
Very, very good. Very good. So you see, this kind of a thing, integration of y dA, as per our earlier discussion, I had mentioned and perhaps reminded you that this is utilized for the calculation of the centroid. Now, this is telling us that this is equal to 0. Okay, so for the calculation of the centroid in general, you use something like this, that y dA integrated over the area is equal to y bar times a, where y bar is the location of the centroid, at least it is the y coordinate of the centroid multiplied by the overall area. Now it is telling us that this integration is equal to 0. Now certainly the area of the cross section is not 0. The implication of this formula is that the y bar is equal to 0. Now the y bar is equal to 0 means that the x-axis means the x-axis, it passes through the centroid itself. Okay, so it is something like this, that perhaps you are considering a square cross section. And now you have considered your x-axis like this and your y-axis like this, which is at the perfect center of this square. So this is x and this is y. Now with respect to this coordinate system, if I ask you to find out the y coordinate of the centroid, what will you write? The y coordinate of the centroid is 0, just like the x coordinate of the centroid is also 0. That is exactly what is happening here. For any generic cross section, you have this formula for finding out the centroid, the y coordinate of the centroid, and that is coming out to be equal to 0. The implication is that the x-axis passes through the centroid. However, we have already chosen, but we had chosen our x-axis to pass through the neutral surface, or to lie along the neutral surface. Therefore, the implication is that the neutral surface passes through the centroid. This is very, very important, okay? The neutral surface passes through the centroid, but it only follows if you had made this choice. If we had chosen, okay, if we had chosen our x-axis to lie along the neutral surface, only and only then it follows that the neutral surface passes through the centroid. So in all the problems that we'll be doing, we will consider our x-axis to be lying along the centroid, to be lying along the neutral axis, and the neutral axis, of course, will then pass through the centroid. It will tremendously help our calculations. When you read textbooks or various kinds of references, you will come across a terminology called the neutral axis. Now, what is that neutral axis? Well, it is very simple actually. If you consider a beam like this, I've already told you that the neutral surface will look like this. That is the projection in the front view. Now, over and above that, you consider any particular cross section. That particular cross section from this side, it will look like this. Suppose this cross section has a rectangular shape. It will look like this, or perhaps it will look like this kind of an ellipse, or perhaps it will look like this kind of a triangle, whatever. Okay, it may have different kinds of shapes, or it may look like this kind of a T-shaped also, which is very which is actually used in practice, or it may be this kind of a I shape. Okay, I'm not just doing things out of my own free will. Okay, so these are the kinds of cross sections which are very, very common. This I section is extremely common in engineering practice. Okay, so you will have the neutral surface intersecting these cross sections, and they will appear in this fashion. Okay, things like this. So what we say is that the line along which the neutral surface intersects a particular cross section, this particular line, this line, this line, this line, all these are referred to as the neutral axis. In many books, not particularly good books, you will find that this neutral surface projection, that is itself referred to as the neutral axis. That is wrong. Okay, strictly speaking, that is wrong terminology. This is the neutral surface projection. The neutral surface cuts any particular cross section over a certain line, and that line is what is referred to as the neutral axis. Please remember this distinction. Okay.
Hello, sir.
Yes.
So can you please tell it once again? I don't think I get the difference between the two.
So this is, we are looking at it from the, so this is what? This is the x-axis, no? This is the x-axis, this is the y-axis. Okay, this is the x-axis, this is the y-axis. My writing app crashed, it seems. Oh God. I hope some of the pages got saved. Let's try again. Okay, you're good. Let me save it quickly. Just give me a second, okay? Okay. So as I was saying, when we are looking at this XY plane, this line, that is the projection of the neutral surface. Okay, so this is not the neutral axis looking at the length of the beam. But when you look at this thing, so what is this plane? This plane, so for these kinds of various cross sections, we are looking at the what plane? Tell me.
YZ plane.
Very good. So this is the YZ plane. So in this YZ plane, the projection of the neutral surface, that is the neutral axis. Okay, so the mistake that sometimes people do is that they call this one as the neutral axis. It is just a terminology, okay? It doesn't really matter. You may call this rabbit, you may call this elephant, doesn't matter. In the big scheme of things, it doesn't matter. It doesn't change the mathematics, it doesn't change the predictions of the beam theory. But, I mean, you wouldn't like it if someone called you by a different name, okay, from what is your official name. So that's what it is. All right, so with
Sir,
this, yeah.
Sir, if the Young's modulus is varying across the beam, then it won't lie on the centroid, right?
It won't lie along the centroid. So if the Young's modulus is varying over the cross section, then the neutral axis is not going to pass through the centroid. Okay, but there are techniques to handle those situations. In fact, I have put in a few problems in your tutorial sheet on that. Okay, I'll give you the hints for how to solve that. Okay, before I proceed, I just want to say something that I have this expression sigma xx, and now I'm moving into the territory of actually solving problems. Okay, even though it may seem that I'm doing theory, but these are the kind of things which you'll have to repeatedly think about while solving the problems. So it is in that direction. What is the maximum value or the maximum, let's say, maximum values of this sigma xx as far as the tensile and the compressive nature of it is concerned? Where do you think those maximum magnitudes of the tensile and the compressive stresses will appear? For what values of y?
At the upper edge.
Yes. For the compressive one, it will be at the upper edge, and for the tensile one, it will be at the lower edge. Okay. So sigma max will be at values which will be like mc by I, where c is like the extremities. Okay. C are the extremities of y. This is very easy but there is an associated concept and terminology present here, which sometimes people use, and it is particularly useful in your professional practice, is that this particular ratio I by C, that is referred to as the section modulus. Okay, so this is sometimes written as S. Okay, this S thing, this is the section modulus. Sometimes information about a particular cross section is given not directly in terms of the geometry, the breadth, the height, and other dimensions. Sometimes it is given in terms of the section modulus. Okay, so given the section modulus of a beam and knowing the value of the moment at a particular cross section, you can immediately just divide the moment by the section modulus to find out the maximum values of the stresses. Okay, so these are the kinds of common things which are used by professional engineers, because in many of the handbooks and the engineering codes, sometimes for common types of cross sections, section moduli are widely available. Okay, so you don't have to carry out repetitive calculations for the same kind of cross sections. Okay, now that we know all of these things, let's start doing the problem. Discussing the problems. Okay, as I told you earlier, it will not be possible for me to go into the kind of detail that I was able to go in my earlier in the earlier weeks. Nevertheless, I'll try to do the best I can. But most of these problems, the challenge in most of them is to do the calculations correctly. Now, on hearing that, I know that many of you would be a little bit disappointed, because you are not calculators and computers. Okay, so when I was a student, I did not like these kinds of problems which were calculation heavy. But you have to understand that it is your responsibility as professional engineers in the making, not just to go about doing fun and intellectually challenging things. Sometimes you also have to do the groundwork of doing the calculations correctly, because people's lives depend on it. Okay. So on that note, we have this rather simple looking cross section where it is essentially a rectangular cross section from which another rectangle has been hollowed out. So it becomes like a box kind of thing. And this box kind of thing, like a beam with a box kind of cross section, it is rather important because first of all, you note that compared to a beam which is completely filled with material, this will be far less heavy. Question is, despite being less heavy, if it can do the job, if it can carry out the responsibility of withholding the structure properly, or letting the structure stand up properly and safely, then why would you need to unnecessarily put material when you don't need it? That is the kind of motivation behind these kinds of structures. Lightweight structures are mostly preferred, especially in the aviation industry, in the aerospace industry, and certainly on Earth itself when you have to construct something like bridges. So in fact, in bridges, you will see that we always, we don't think much when we are traveling on a bridge, but beneath the road of that bridge, there are structures. And the structures which are holding up the roads of the bridges are these kinds of box beams. They are actually referred to as box beams. They have more sophisticated shapes, but essentially they are box kind of structures. Okay, so here you just have to find out the second moment of area correctly for this kind of a problem. Okay, so here the challenge is just to find out the I correctly. And this I can actually be found out very nicely by doing a I1 minus I2. What is this I1? This I1 is the second moment of area of this entire outer thing, assuming it to be completely filled, and this I2 is the second moment of area of this thing, of this inner rectangle, assuming it to be completely filled. And this minus business, it takes care of this hollowing out. Now, who can tell me what is the formula for this I1 or I2, or in general I for a rectangular cross section? For a rectangular cross section, which is like this.
So a square plus b square divided by 12.
Let me show the dimensions. कहाँ से बोलोगे नहीं तुम? Okay, so the breadth is b, the height is h. Now you tell me, what is the I for this, for the rectangular cross section?
So 2h cube b by 3.
It is actually 1 by 12 bhq. Okay. You tell me one thing. This is just a formula, okay? I mean, you just have to spend a little bit of time if you want to really derive it with your own hand from this I is equal to integration of y squared dA. But more importantly, what I want you to think about is that regarding the centroid and the neutral axis. Okay, you see, initially when we had started our discussions, if you go back to our absolute first slide, let me first save this thing and then go up. The absolute first slide, I had mentioned that we are going to consider the kind of cross sections which have a certain plane of symmetry over which there is this right-left symmetry. It is not essential for us to have a symmetry about any horizontal axis. It is not necessary for us to have that. In order for the development of the theory, it is not necessary. So for symmetric bending, symmetric pure bending, we only need the existence of this kind of a symmetric plane about which there is right-left symmetry, and we also have to ensure that the moment, the applied moment, is being applied on that plane or along that plane. That is all that we required. There was no requirement of any symmetry about any horizontal axis. But it is very much possible that we have cross sections which have not only this kind of a horizontal symmetry, rather they have some kind of a vertical symmetry. Meaning that suppose you take a triangular cross section. This triangular cross section has only one plane of symmetry, this one, about which there is right-left symmetry. So a triangular cross section very much falls within the purview of our entire theory. It can be applied. So our theory can be applied to this kind of a triangular cross section. Now, suppose we have this kind of a rectangle. Now this rectangle, it certainly has this kind of a left-right symmetry, but at the same time, it also has the top-bottom or the up-down symmetry. So this is almost like a, not almost, this is a bisymmetric kind of structure or cross section. Okay, or it is a cross section having double symmetry. So certainly our theory will be applicable very much in this kind of cross section also. Similarly, you may have an elliptical cross section, a special case of which would be a circular cross section, and even in this kind of a thing, you will have a double symmetry, and our theory would be very much applicable here. So all of these things are good, and you will encounter these things in your problems. But most commonly this one. Earlier I had mentioned about a T-shaped beam. Now this T-shaped beam, again, in terms of the symmetry, it is of the same category as this triangle, because even though there is horizontal symmetry about this axis, there is no axis about which there is vertical symmetry. However, for the other very common kind of cross section which is used in engineering practice, this kind of an I section. I call this an I section because literally this looks like the English letter I. This looks like the T section. This is the T section because it looks like the inverted T. You will also have things like the L section. Okay, you will also have cross sections like this L, but this L section will not, like our theory will not be applicable here because it does not have any vertical horizontal symmetry. Okay, but this one, it has both this horizontal symmetry and the vertical symmetry about these axes. Okay, so these are the kind of things which you should immediately think about before solving any problem. So we are dealing with this rectangular cross section, and all you have to do is substitute the appropriate values of B and H in this I1 and I2, considering this outer rectangle and this inner rectangle, and then you can go about finding out the stresses at the points A and B, because note that this 10 kilonewton meter moment value is given to us. Okay, so all that you have to do is write this sigma xx is equal to minus my by I, where note that this I is this I1 minus I2, and y will be calculated from the neutral axis, which also happens to be the centroidal axis. So please note that if you consider this kind of an axis, which is actually the z axis, this is the y axis, and this here is the z axis. Sorry, the x axis. Sorry. This is the x-axis. So the diagram is exactly like what we have been dealing with in our general theory. All right. So this z-axis, it is also the neutral axis. Mind you, what I told you about the neutral axis. So literally, the xz plane is the neutral surface. Okay, so here the xz plane is the neutral surface. It is also the, so this x axis or the z axis, it is passing through the centroid. The y axis is also passing through the centroid of this cross section, this nice doubly symmetric cross section. Okay. Do you have any question about this? This is rather straightforward, but if you have any question about it, please do tell me.
So in calculating the value of I, we are calculating about z-axis, right?
We are calculating about the z-axis, yes. Anything else?
So about the z-axis means, can we not take axis along point B or along point?
Please repeat your question.
So can we not take axis along B and along A? Parallel to z-axis.
So if you take your axis along A and B, there is nothing mathematically preventing you, but then you would have to derive the entire theory starting from that, because you note that when we were in this particular slide, this entire relationship epsilon x6 is equal to minus y by rho, it depends on the fact that you are calculating this distance y from the neutral surface along which the x-axis has been taken. So if you change your choice of the x-axis from the neutral surface to something which is lying on the top of the on the top point of the cross section, the bottom point of the cross section, the entire calculations, the entire derivation will change. But why would you do that? Okay, why? I mean, life is short. You try to make your life as easy as possible. Why would you unnecessarily complicate it? Okay, that's the simple reason that we don't do it. Just give me a second. I'll switch on my okay. Let's get back to the problem. Okay, so this is the second problem from our tutorial sheet. And here we have been given this kind of a shaft, which is supported by journal bearings at A and B that only exert vertical reactions on the shaft. You are familiar with these statements from earlier. The question actually is that determine the smallest diameter D if the allowable bending stress is sigma allowable is equal to 180 megapascals. Okay, so we have been said, or we have been told, that the magnitude of sigma xx that we are going to calculate, that's going to be less than this sigma allowable. This is the heart and soul of the problem. Okay, I'm sure everyone understands this. Question is that in order for the worst case scenario, which we must investigate, in order to ensure that even that worst possible or the largest possible value of the sigma xx should not exceed sigma allowable, we must be able to take the absolute largest magnitude of this sigma xx. Now the absolute largest magnitude of this, earlier I had said that at a particular cross section, this thing will be given by I. So at a cross section, at a particular cross section, the C value depicting the extremities of the Y value, that will be giving us the maximum magnitudes of this sigma xx, tensile and compressive. However, you also have to understand that the value of the bending moment may change as you go along the length of the shaft. So for the absolute maximum, okay, for the absolute maximum, you also have to take the maximum value of this bending moment. So effectively, what you have been asked to do in this problem is a two-part business. First of all, you have to determine the maximum value of the bending moment using the same kind of principles which you have been using in order to solve the problems from the previous week. First, you draw the bending moment diagram, and then you find out the maximum magnitude of the bending moment. In fact, in your assignment also, I have asked you to do a similar sort of thing. Okay, as part of one of the questions, you have been asked to find out the maximum value of the, I think, the shear force and the bending moment, things like that. At least in the Moodle version of the question that I have said, there are one or two parts like that. So it says in a similar sort of situation, you also have to find out the maximum value of the bending moment. And on top of that, you have to take the extremities of the cross section. Please note that this cross section here is this circle. Nice, perfect circle. Okay, so all that you have to do is take the distance of d by 2, because the neutral axis would be passing through the center of the circle, because the center is the centroid of the circular cross section. Okay, so the circular cross section has its center as the centroid. The neutral axis is going to pass through that centroid, and you are supposed to find out the maximum value of the stresses at extreme distances from the centroid, which happens to be d by 2, either way, either top or bottom. All right. So do you have any question on this? I expect that you won't have any conceptual questions on it, but when you do go on to solving the problems, there the challenge will be to do it correctly. Okay, so again, I'm telling you, conceptually, once you get the hang of the theory, like the entire story behind the development of these formulas, these problems are not conceptually hard, but the difficulty only lies in getting the correct values. Still, there are certain things which I will want you to think about. One of them has to do with this problem. So each of these problems that I've selected has been for a certain reason, to highlight certain aspects of engineering beam design, or some important thing which I would like to highlight. So here we have been given two designs for a beam. Okay, so consider yourself to be a design engineer. You have to go for one of these choices. Which one will you do? Okay, and sorry about the typo here. Determine which one will support a moment of m is equal to 150 kilonewton meter with the least amount of bending stress. So see, in terms of the actual solving of the problem, all that you have to do is first take up part A, calculate the value of I, and then you find out the maximum value or the minimum value of the sigma xx. You find out the, compare these two and find out the sigma xx, which is the minimum, and say that. Answer, it has been provided as sigma, the design B. If you do the calculations correctly, you will also get the answer. I trust all of you can do that. That is not why I have chosen the problem. The reason that I have chosen is to take a close look at these two things. Okay, there is a subtle difference in the way that they have been shaped. Here, this middle stem that has been made thick, but the top flanges, they have been made, so these are referred to as flanges, they are quite thin. On the other hand, here, this web, okay, this web or this middle stem that has been made quite thin, and these two things, the top and bottom, they have been made thicker. It is from the answer, we know that this design B is better, but saying that something is better makes no sense unless you say what it is better at. So it is better at producing the least amount of bending stress. Good. But as a design engineer, should you always be satisfied with such a very restrictive point of view? Answer is no. It is good that you are investigating the least amount of bending stress which will be produced from two alternative choices of design. But the ultimate decision that you will make should not be based solely on one such criteria, that it is producing the least amount of bending stress. So what other possible things should you be thinking about? Now, you have not done all the chapters of mechanics of solids, so it may not be possible for you to think about it right away. So I will give you a hint. You see, these kinds of structures will definitely be subjected to some kind of transverse loading. Transverse loading means the loading will take place from the top like this. When the loading takes place from the top like this, and their line of action will definitely be passing through this stem, because as we have said that we can only handle things as far as our current theory is concerned when the loading takes place in the plane of symmetry. So it will be, this line of action will be passing through this stem. Now, from the point of view of this stem, which is very thin, this is not a particularly safe thing to consider, because there is such a concept as buckling. If you consider a very, very slender structure, and you subject it to compressive loads from the top and the bottom, then there is a chance that this structure will buckle. Buckle means this structure will get bent out of shape like this. And in fact, we do have a chapter on buckling, which will be covered near the end of this semester. So this kind of a bending deformation, which is out of the plane of this thing, is not at all desirable. There are certain situations, and currently in the nanotechnology world, people are striving to actually take the help of buckling to make designs which are beneficial, but those are very sophisticated, exotic kind of designs. But in common kind of engineering structures for beams, for shelves, these kinds of buckling deformations are not at all desirable. So even though the second structure may look to us that it is very good in terms of bending stress, but from the point of view of another aspect of engineering design, it is not at all good. So as a design engineer, time and again, I'm telling you, you will often have to come to a trade-off kind of decision. What is good on one hand, what is good on other hand. Maybe the actual design is neither A nor B. Maybe it is somewhere in between. Nobody is going to tell you what that is. That is why the job of a design engineer is so very critically important. It is like a combination of scientific mastery, engineering craftsmanship, and like artistic sensibilities. Okay, it is a combination of everything. You really, really have to be good. Does anyone want to say something at this point? I heard someone unmuting their mic. If not, let us go on to the next one. Okay, so we have this T-shaped cross section. This is the T-beam. This T-beam is rather common in engineering practice. You may even see things like this if you go to any engineering construction site. So if you visit any engineering construction site, and I really wish that you were able to visit IIT Kharagpur at this point, because all around the campus there are a lot of engineering projects going on, because a lot of buildings are being constructed here and there. So you would have been able to see many of the kinds of actual beams which are used. One of the most common sections which are used is this kind of a C section or a channel section, where the cross section is like this. The other one is that I type of cross section that I told you about, but this T-shaped cross section is also not that uncommon. But this is very common. The I-shaped cross section is extremely common, not just in India, but even in the US, the UK, I mean, of course, in Germany, all around the world. Okay. But here we have this thing. So how do we go about doing it? Well, first of all, unlike the previous problems where we did not have to worry that much about the neutral axis passing through the centroid, here our first job will be to first set up the location of the centroid. That is important. Okay, first locate the centroid. Now this is important because without the knowledge of the location of the centroid, you will not know where to set up your z-axis and the y-axis. Why is that important? You first locate the centroid, make the z-axis pass through the centroid. And only when you do that, only when you make the z-axis pass through the centroid, can you go about finding out the I. So you see, for the formula of sigma xx is equal to minus y by I, this I is with respect, as one of your batchmates had already asked in the previous problem, that this it is with respect to the z-axis. So we first need to know where to locate the z-axis. The z-axis has to be through the centroid. So given any particular cross section, if it is not possessing double symmetry, we must first find out the location of the centroid. Okay, so you first find out the location of the centroid, then you find out the I, and then once you have the I value, then you go about applying this formula. Okay, and for that, remember that this y has to be calculated with respect to the centroid. Okay, so I think instead of just describing it like this, it will be better if I at least outline some of the calculated values, but I'll do that tomorrow, and of course continue with some of the other problems, especially those connected with composite beams where there is a difference in material properties across a particular cross section. All right, on that note, I will end today's lecture. Thank you very much. We'll meet tomorrow. Please go to the next class.
Thank you, sir. Thank you, sir.
Thanks.
Sir,
Thank you, sir.
two respective tests in the Moodle.
Thank you,
And
sir.
in the website.
Someone was saying something.
Sir, I was asking that in Moodle website it is given that two respective tests will be done. So
No. So it is exactly like the procedure of basic engineering mechanics